Swayam Prabha. Digital India. Educated India.
So, let us continue to talk about the science based foundation of steel making, and I have already briefly told you about the relevance of thermodynamics and try to introduce certain key concepts of thermodynamics. And as I have mentioned, that it is not possible to cover each and every topic, but at least in the context of prediction of feasibility of a reaction or equilibrium calculation, I have tried to make use of certain concepts and demonstrate to you that yes, with the knowledge of equilibrium, knowledge of activity composition relationship, etc., you will be able to formulate equations, use thermodynamic data, and then make prediction about the state of equilibrium in terms of temperature, pressure, and composition. Now, on thermodynamics, there are various textbooks available. For example, a nice UG textbook that we follow at IIT Kanpur is the textbook by Professor Gaskell. There are innumerable other metallurgical thermodynamics textbooks, and I urge that you go through that text in order to get a comprehensive idea of the subject of thermodynamics. Following thermodynamics, now I would like to talk about fluid dynamics. Now, steel making per se, from the stage of basic oxygen furnace down to continuous casting, at every stage we have processing and transfer operations, and these are controlled by fluid flow, in the sense that melt flow or flow of steel in reactors like BOF, EAF, ladles, turn dish, and mold will control the interfacial reaction rates, will control the mass transport within the fluid, will control refractory metal interactions and refractory erosion rates. You name a process which is occurring in the steel making reactor, and you will find that at the root of that problem, the fluid flow really plays a decisive role. Now, we all know that, for example, if you introduce stirring, the mass transport and mixing is going to be very, very intense. For example, if you take a cup of tea, add a spoon of sugar, and you do not stir it, then the sugar does not dissolve. Okay? So, to get a homogeneous mixture of sugar in your tea, you have to stir it vigorously with a spoon, and then only you get a mixture. And that is why in every stage of steel making, as we see that we try to deliberately introduce stirring, either by injecting an inert gas or a reacting gas or the metal falling from a certain height, and this creates enormous amount of convection current in the system, and that convection current aids in controlling the rate of heat and mass transport and various other processes. For example, you name it, and the process is going to be have most of 99% of the cases you will see that the rate of the process is really enhanced by the fluid dynamics prevalent in the reactor. Now, intensity of flow is very important for us, and the intensity of flow can be regulated or depends on the system geometry. It depends on the power, which is stirring power, we say, which is being fed into the reactor, and the level of intensity will eventually determine. For example, if you have added an alloying addition and you want the alloying addition to melt and dissolve in the bath, you invariably will conclude that greater is the stirring rate in the system, greater is the movement of the fluid, more will be the rate, or faster will be the rate of melting and dissolution. So, there is no ambiguity as far as the relevance of fluid dynamics in steel making. It is a very complex subject. You require very good knowledge of maths, you require very good knowledge of vector and tensor in order to understand the subject, and it is the scope of the subject is enormous. You can run, there can be diverse topics which are involved, starting from simple laws of fluid dynamics to complex flows, turbulence, and etc. And the scope is enormous, and possibly it will be very difficult for me to introduce all the concepts, but I am going to try to highlight the role of fluid flow. And how can you know? Our objective is to know the state of fluid motion in the reactor. Having obtained information about fluid flow, how can you use that information to to predict the rate of metallurgical processes or steel making processes is our essential objective, and I will hover around that central point, that how to get some meaningful information about the state of fluid motion in steel making reactor, and to be able to do that, what information do you require at our end. Now, the intensity of flow in steel making reactor varies appreciably from one process to another process. So, we understand that the nature of fluid motion in steel making reactor are going to be different. By nature, I am saying that if the intensity of fluid motion is very small, maybe we can get a laminar or a transition flow. On the other hand, if the intensity of motion is vigorous, in that case we can have turbulent motion in the system. Now, I have mentioned to you that, for example, in tun dishes we have a flow of the order of centimeters per second. When you have a furnace tapping operation, we may have flows of the order of few meters per second. So, therefore, the state of fluid motions in reactors are different, and invariably we will see that because the size of the reactor is large, and that the kinematic viscosity of steel is very, very small. So, therefore, the Reynolds number of the flows are appreciable under steel making conditions. So, as a thumb rule, we can say that flows in steel making reactors are going to be invariably turbulent. What are the other characteristics of the flow? Other characteristics of the flow would be, is the flow one dimensional, two dimensional, or three dimensional? Because now, for example, in a pipe flow problem, the fluid moves, comes at one end, leaves at one other end. This we say as there is a predominant direction of motion. But in steel making reactors, these are all three dimensional reactors. So, there is x component of fluid flow, also there is y component of fluid flow, there is z component of fluid flow. Okay. So, all three components of motion are going to be prevalent. So, simplification and idealization in terms of dimensionality of the problem is not going to be very much advantageous in our case, and we will find that the flows in majority of the cases are going to be three dimensional in nature. Pipe flow type problems or flow over a flat plate type problems, these classical flow problems will never be encountered under steel making situation. Particularly if you look at the processes starting from BOF to the continuous casting, nowhere approximation of a two dimensional flow or a one dimensional flow will be tenable. Now, is the flow steady or the unsteady? The next question that we ask, that now depending on the process, the flow can either be steady or unsteady, because we know that if flow becomes when the process is just started. For example, the ladle is sitting, metal is sitting in the ladle, and the moment I start to inject gas, from that moment onwards the velocity is going to change as a function of time. At some point of time the velocity will become constant. So, that looks something like this. So, for example, if you plot velocity at a location versus time with gas injection in a ladle, okay, small little figure I draw. So, I introduce a gas here, and then the flow develops, and you see the flow goes something like this. So, this is basically the period which is called the flow establishment period or the period of transience. That means, we have started to blow gas, and then for some time what happens is we have a power which is the buoyancy power which we input through the gas, and it accelerates the fluid, and at some point what happened is the energy supplied by the bubble is balanced by the losses through various mechanisms, and then we obtain a steady state process. Just like the way you take a kettle of water and you try to heat it. So, initially the temperature of the temperature of water is going to be increased, and at some point of time the rate of heat input to the kettle will be exactly balanced by the rate of heat loss, and then you are going to hit a constant temperature. That is the characteristics also exhibited in this particular case. From 0, the velocity is 0. So, the velocity starts to increase as we introduce gas, and then eventually the velocity becomes a steady state. So, it depends on the process in which we are looking at. If you are looking at the initial period of gas injection, the flow is unsteady. If you are looking at a long duration of gas injection, in that case we can say that the flow is steady. Furnace tapping operation, continuously the bath is being filled up. The ladle is empty initially, metal is coming from the furnace, it is being poured into the ladle, and as a result of which the bath depth increases. And as the bath depth increases, the distance between the lip of the mouth as well as the free surface or the surface of the liquid continuously decreases. As this level increases, So, the distance of separation between the furnace lip and the level of melt continuously decreases. So, as a result of which the flow phenomena in the system throughout the tapping operation remains unsteady. So, we will not be able to just say always that the flow is steady or unsteady. Depending on the scenario, the flow can be steady or flow can be unsteady. Okay. Now, having said so, we understand that our flows are going to be multidimensional, mostly three-dimensional. Flows are going to be unsteady. Flows are steady depending on the process, depending on the duration at which we are concentrating. Flows are most likely going to be turbulent. Now, we have non-isothermality also in steel making reactors, because I have been saying all along that we know that we have a furnace or a ladle, and then through the wall or through the mouth the heat radiates. So, as a result of which we can expect that if we have a VOF converter here, particularly when there is not much stirring, okay. So, I can say it is going like this. So, there is expected to be some gradient in temperature, and this difference in temperature will depend on how good a stirring is there. This difference in temperature will be minimum if the stirring in the bath is very, very good. If this difference in temperature could be pronounced if the stirring in the bulk of the metal is not same. So, there is difference in temperature, there could be difference in temperature in the system. Ladle which is being held at some, there is no gas injection, nothing like that. So, the ladle contains molten metal, and then there is going to be heat loss through all the surfaces, and as a result of heat loss there is going to be difference in temperature between various locations. So, this will have a higher temperature, this will have a lower temperature because of heat loss, and as a result of which we have differential temperature, which makes the process non-isothermal in nature. So, we are not talking of isothermal process. So, the fluid flow, melt flow is going to take it under non-isothermal condition, and non-isothermality, as you must be knowing from your basic transport phenomena, may introduce some kind of a thermal buoyancy into the system. And what governs thermal buoyancy? With vis-a-vis the forced convection, free to forced convection is the ratio which we say the Grashof over the Reynolds number square. It is this term that will say, for example, whether we have a strong free convection current or strong forced convection current. Grashof's number is a measure of the buoyancy, Reynolds number is a measure of inertial forces. So, calculating this ratio, we should be able to find out that whether free convection is important or not. So, therefore, I may have forced convection when I am introducing a gas into the system, or I may have some alternative form of stirring, electromagnetic stirring, okay. And also I may have free convection also, and free convection particularly because of thermal gradients or because of concentration gradients, we may have free convection currents in the system. So, whether free convection is important. So, there may be some situations in which there will be no forced convection, for example, holding period in a ladle where there is no gas is being injected into the ladle, okay. In that case, I will have no forced convection, but if there is any flow at all, that flow is going to be attributed to free convection. On the other hand, when I am going to have a gas injection into the ladle, I will have both forced convection and free convection, because free convection will be there because of temperature differential in the system, thermal stratification in the system, and forced convection flow which is going to be there because of the introduction of the gas itself. Now, whether free convection effects are important or not, as I have mentioned, this will be dictated by this particular number. Now, coming back to the issue of non-isothermality. So, therefore, in some systems where we have no strong forced convection current, in that case the non-isothermality can affect our fluid flow, because we know that difference in temperature will cause difference in density. So, heavier density fluid will go down, lighter density fluid will go up, and that creates a natural convection current under the influence of gravity, and that is called natural convection or thermal buoyancy. And so therefore, any isothermality may also affect the fluid flow condition in the system, that can precipitate into fluid flow in the system naturally because of thermal gradient. Similarly, if you have concentration gradient, okay, that concentration gradient, for example, at some point you have little amount of carbon, at somewhere you have bigger amount of carbon. So, more carbon means less density, less carbon means higher density in steel. So, therefore, you are going to have a differential motion, and as a result of which you have a buoyancy which is not thermal buoyancy, but which is we call as a solutal buoyancy. So, in still making systems where we have concentration gradients in the system, where we have temperature gradients in the system, we will see that the fluid flow in the system or melt flow in the system could be a result of the combined effect of thermosolutal convection also in addition to forced convection. For example, particularly if you look at the continuous casting, suppose you are considering a bloom casting and you know that there is a metallurgical length, and this bloom casting we go towards the lower part of the metallurgical length where we have little bit core of liquid and the rest everything is solidified, and there virtually you do not see the impact of the SEN, because the SEN is located much high. Metallurgical length we are talking about 10 meters or 8 meters. So therefore, I am talking about a distance of 7 meters down the meniscus where we may note some weak motion, and that weak motion, it is now well known, is as a result of thermosolutal convection. Okay. So within the mold region in continuous casting, the flow is going to be primarily driven by forced convection because of the impingement of the incoming jet of molten steel. On the other hand, towards the lower part of the strand where we have still some molten metal, and there if you see any noticeable motion, and that noticeable motion is going to be as a result of thermosolutal buoyancy. That means there is a difference in temperature, there is a difference in concentration, and both this difference in concentration and difference in pressure, difference in temperature have precipitated into flow. So non-isothermality can be a big factor in our fluid flow, in our melt flow analysis. Concentration difference also can play an important role in our fluid flow understanding. Most importantly, however, is that in a steel making reactor, be it little, be it primary steel making converter, BOF or EOF, you have multi-phase interaction. It is not just flow of one fluid. We have gas is flowing, okay, we have liquid is flowing, we have slag is flowing, we have added solid, the solid may be moving in the system, okay. So it is a multi-phase system. So therefore, to summarize the nature of steel making flows, I would say that steel making flows are multidimensional. Steel making flows could be transient or steady. They are invariably turbulent. Free convection, or I will say thermosolutal convection. Thermosolutal convection is important. Thermosolutal convection. So multidimensional, transient or steady, turbulent, thermosolutal convection plus multi-phase flows. You name a complexity, you will find it in steel making. And also, for example, in some cases what we see that on top of this flow, the domain either shrinks or expands because of solidification and melting phenomena, which is the consequence of heat transfer itself. So the fluid flow or the flow of melt is not as per se is a unique phenomena, okay. It is actually interrelated to so many other things which are going to influence the flow, okay. It is not just like a simple flow of a pipe flow or a homogeneous fluid moving in a tank. No, it is not that kind of a flow. You name a phenomena, solidification, multi-phase, thermosolutal convection, all these features, characteristics are going to influence the flow. So therefore, we have to understand all these things in great detail in order to address the fluid flow or fluid dynamics in steel making reactors. So the subject at hand is an extremely complex, and it is going to be, the scope is going to be enormous, as you see so many types of concepts are they are particularly the subjects of turbulence, the subjects of multi-phase flows, the subjects of thermosolutal convection. These are in a free convection. These themselves are a huge topic with enormous scope, and on each of these subjects maybe more than one semester course can be run, and you can imagine therefore that the effort and time that will be needed in order to master the subject of fluid dynamics and then apply the theory and our understanding to the reactor in order to see how does the fluid flow really influences the process. And as I said in the beginning, that our objective is we have to know about the state of fluid motion somehow in the system. So, this is cutthroat statement. Okay, the theory stays in its place, the textbooks are in their place, but as a steel making engineer, steel maker, my objective is to know the flow. And why I wish to know the flow? Because I want to calculate melting rates, I want to calculate desulfurization rates, I want to calculate refractory erosion. All these things are my basic aim. Okay, but in the background I see that these are intricately related to fluid dynamics in the reactor. So, therefore, I have no option but to study the subject of fluid dynamics in great detail, so that I can really address the rate of the metallurgical processes that are taking place in the steel making reactors. Now, how can you predict or know the state of fluid motion? I am not going to discuss, the theory is enormous. So, it is not possible for me to discuss the theory. So, I am addressing it that from the end point objective, that how do you know the fluid flow, how can you calculate the fluid flow, what are the resources that we need. We have, of course, many textbooks which we can follow, understand the fundamentals, and assuming that we have the fundamentals, proper fundamentals, the questions that I pose before you is, how do we know the state of fluid motion? This is the basic or the essential problem. Concepts like parallel flow, Newton laws of viscosity, Navier-Stokes equation, irrotational flows, then simple parabolic flows, creeping flows. These are very essential in order to develop a comprehensive framework for our understanding. But assuming that we know, our fundamentals are ready, we are ready in terms of our fundamentals. The question is now, how do you know the state of fluid motion in steel making reactors? Now, in any system, we can get information about a given phenomena either by carrying out experiments or by carrying out calculations. Okay, we can develop a simple mathematical model, for example, and then we can find out that what is the state of fluid motion, or we can use a probe or a sensor and then find out that what is the state of fluid motion. So, we have two different standpoints. Now, one is experimentally we can obtain the fluid flow information about the flow, and number two is theoretically, provided an adequate theoretical background exists. Okay, in many of the cases, because of the complexity of the flow, we are going to see that an adequate mathematical description, adequate means near perfect mathematical description, still does not exist. Okay, and therefore, as I have mentioned, or as you might be knowing, that if the mathematical description, if the theoretical background is not right, if the mathematical model is not correct, in that case we will not be able to predict the process correctly. Now, coming back to this point, experimentally it is perhaps extremely cumbersome. It would be extremely cumbersome to determine or map the velocity field in a BOF reactor. We may not have probes, because we require probes which you have to immerse. Steel is opaque, so we cannot see what is going on, and that we may not have probes which can work on a sustained basis under such a rugged environment of 1600 degrees centigrade and in a huge reactor size. So, perhaps we can say that experimental determination, rigorous experimental determination or mapping of flow field in steel making reactor as of now is not possible. It is going to be enormously time consuming, it is going to be very difficult, it is going to be very expensive. So, we can rule out the possibility. So, only possibility is that we can calculate possibly the melt flow phenomena from a theoretical background. Steel, as we all know, is a Newtonian fluid. So, the theory of Newtonian fluids can be applied, and although molten steel would exhibit most of the time incompressible flows, but if you are injecting gases to the bottom, in that case the gas density can change enormously because of the difference in temperature, and some compressibility effect can come as far as the motion of the gas is concerned, while the flow of liquid is concerned, the compressibility may not have direct relevance. Of course, the motion of gas would influence the motion of the liquid there. So, if the gas compressibility influences the motion of the steel, motion of the gas, okay, in that case there is going to be an indirect influence of gas compressibility on the movement of liquid steel. Now, how does, when you inject gas, how does the liquid moves? The liquid moves because of the application of drag forces. The bubbles move or the gas stream moves, it drags along with its fluid, and therefore, there is going to be momentum exchanges between the gas and the liquid. There are going to be various surface forces through which the gas and the liquid are going to interact, and they interchange momentum through their surfaces, and as a result of which the bubbles or the gas, as it rises, okay, it imparts momentum to the liquid and the liquid recirculates. That concept perhaps you know from your elementary transport phenomena. So, we have to seek for a theoretical background. Now, we can first say that, well, look, when you are talking of a theoretical background and we want to know the velocity, and this velocity comes from, basically expression comes from the Newton's law of motion. So, the theoretical background is formulated on the basis of Newton's law of motion, and where we say that the net acceleration produced is equal to the algebraic sum of the forces, and what are the forces that are acting in the fluid one may take into account. And when we consider that pressure, inertial, gravitational and viscous forces are the only relevant forces which are acting in the fluid element, and then if we carry out a control volume based analysis or derivation, then we can derive what is known as the conservation of momentum. We can carry out a conservation of momentum, or which is essentially, and this gives rise to what is known as the Navier-Stokes equation. So, the basic framework based on which the velocity fields within steel melt is going to be calculated is the Navier-Stokes equation, and we all know that in the Navier-Stokes equation we have other expressions like Stokes law, etc., which are incorporated. So, this also statement is not unfamiliar to you. You know this statement, a statement of Navier-Stokes or the Navier-Stokes equation from your knowledge of transport phenomena. So, we have an overall continuity equation and the three equation of balances. So, because we are talking of multidimensional flow, that means we are going to have three different components of flow. If you have x, y and z, okay, y, z, x. So, we have a Vx component of flow, we have a Vy component of flow, we have a Vz component of flow. Okay. So, there is a Vx conservation of momentum, there is a Vy conservation of momentum, there is a Vz conservation of momentum, or we can say there is an x component of motion, equation for x component of motion, which is essentially the Newton's law force balance equation applied along the x direction. Then we can say there is a z equation of motion along the z direction, which is a momentum conservation equation along the z direction, and then we can say similarly that there is a conservation of momentum or equation of motion along the y direction. So, we have three different equations, therefore, when we talk of a multidimensional or a three-dimensional scenario. Okay. And these three equations, as we will see, for example, I can write down, if I write down the unsteady state equation, for example, one such equation I can show that I write it in a conservative form, three-dimensional. So, this is the x component of motion that I am writing actually, and so these are the viscous terms now that I am writing. This is the pressure force or pressure gradient term, and this is the viscous term along the x direction. This is the viscous term along the y direction, and this is the viscous term along the z direction. And note that I have considered that, well, the system under consideration can be described by, so we have selected, we assume that the system under consideration can be written or expressed in terms of a Cartesian coordinate system. So, we can have the Navier-Stokes equation in cylindrical polar coordinate system, we have in spherical coordinate system, and then we have rho g x. Okay. And obviously, if you are saying that it is a gravitational component, the component of Gx along the x, G along the x direction is Gx, and that is in this particular case, if gravity is the force, is actually is equal to 0. Now, so we have x ux component, x component of Mo equation, then we similarly will have a term y component, and similarly we have third equation as, and note that these equations I have written in terms of in the unsteady state mode, because I have a net rate of accumulation term, this derivative term becomes equal to 0. So, conservation of momentum, if it is a 3-dimensional flow, we get 3 such equations. Okay. And on, because in these 3 such equations we have unknowns are what? Unknowns are ux, uz, uy, there are 3 unknowns, but on top of that we see that there is another unknown, pressure, which is to be calculated as a part of the solution. So, the fourth equation which is needed always is the overall continuity equation. And if I say that the flow is incompressible, then I can write that, well, this equation goes like note that I have written this equation for an incompressible flow. I have written this equation for a Newtonian fluid, because of the viscous term, stress is taken to be directly proportional to the strain rate. And now I have 1, 2, 3, 4 equations, and I have 1, 2, 3 and 4 unknowns. So, these are my 4 unknowns. This is 1, this is 2, this is 3. Okay. These are the 4 unknowns, and I have 4 equations. So, therefore, if I can solve these equations with the correct number, of course, these are partial differential equations, I will require boundary conditions or initial conditions to be expressed, okay, appropriate number. Assuming that we have the correct number of boundary conditions, we should be able to solve this equation. Note that this equation, it is valid for multidimensional flow, it is valid for transient flow, it is valid for Newtonian fluid, it is valid for incompressible flow, and it is valid equally for both laminar and turbulent flow. No restrictions have been made. But if we try to solve this equation, I will come back to this issue a little bit later, more rigorous, in more detail. If we try to solve this equation for turbulent flow, we are going to have some problem, but we will talk about it a little later. Right now, we see that we have 4 equations and 4 unknowns. So, that means it is a well defined problem, assuming that we have the right number of boundary conditions. Now, these differential equations, as you can see here, are non-linear differential equations, because you see that you have product of the velocity terms, which is a second order term, and also these equations are interrelated. For example, this is this equation, as I have mentioned, this is a balance or conservation of momentum along conservation of x momentum. So, that is this particular equation. Second equation is conservation of y momentum, third equation is conservation of z momentum. So, if you look at these equations, they are essentially multidimensional, and you can see that they are non-linear, and also in this equation it is a x momentum conservation equation, but you see the y velocity component and z velocity component appears. So, therefore, this equation and this equation are mutually coupled. Okay? Both x velocity component depends on y and y velocity component depends on x, and same is true for the z component also. So, therefore, you cannot solve these equations independently, they are mutually coupled equation. All the 4 equations have to be solved simultaneously, and you therefore cannot solve them by hand. You have to take care of what is known as a numerical method in order to solve this equation. And this is itself, the numerical solution of such complex differential equation itself is a very interesting, important subject in this particular context, which we call as a computational fluid dynamics or CFD. So, it is an entire subject on its own, and this is also an area beyond. When you talk of we need some expertise in fluid dynamics, we have to know fluid dynamics. We, in the context of metallurgical problems, we not only stop at the analytical work, we have to look at the possibilities of numerical solutions, understand the numerical solutions well, and therefore, when you say that we have to have some expertise in fluid dynamics, we will have to know the subject of CFD also, or computational fluid dynamics also very well. Now, you can have just 4 equations, for example. On top of this, as I have mentioned, that if you have thermal buoyancy, if you have solutal buoyancy, in that case the flow is going to be influenced by thermosolutal convection also. So, the flow is going to be related to heat transfer, and the flow of heat also from one point to another point is going to be related to fluid flow. So, therefore, if there are thermosolutal convections which are important in this particular case, we understand number 1, the flow will then depend on the concentration gradient, flow will depend on the temperature gradient. Also, the flow of heat or flow of mass from one point to another point is going to be related to the fluid flow also, because the flow of fluid or melt will take material from one point to another point, because it will depend on the rate at which material will flow from this point to this point, or heat will flow from this point to this point, will depend on the extent of or the convection current present in the system. So, in many situations where thermosolutal convections are important, we will see that the fluid dynamics equation cannot be solved in an isolated fashion. They have to be solved with heat transfer equation, mass transfer equation, which will constitute a more comprehensive and more detailed mathematical model. So, therefore, the point that I am trying to make is that we are talking of solution of not just 1, 2, 3, 4 equations in steel making systems where we have so much of complexity. In that case, invariably we will see that in many situations we are going to have more than 6, 7 or 8 equations, and solving these equations, you can imagine that when you have all these processes, solidification and electromagnetic stirring, for example, in continuous casting, okay, you have to solve the electrodynamics equation also, and then additional equations will come into the picture. So, we are talking of solving of a number of nonlinear mutually interlinked partial differential equations, and solving them. Now, you have to use computer to solve them, and every time if you want to write computer codes to solve these equations, write a program, debug the program, it is going to take really long time. So, we have now very important software platforms which are available to us, and these softwares are basically CFD softwares, computational fluid dynamics softwares, dedicated exclusively to the modeling of the kind of flow that we are talking about here. They can model multi-phase flows, they can model multi-dimensional flow, they can model turbulent flow, and so you don't write a computer program, but you formulate the problem, then you go to the computational or CFD software and use the CFD software to configure your problem, and thereafter you can solve the problems very conveniently. So, when I talk of expertise in fluid dynamics, I talk of some knowledge in the theory of fluid flow. I am talking of some knowledge of on computational fluid dynamics and some knowledge on CFD software. But most of the time, in order to know the state of the fluid flow, you will see that your theoretical background, your theoretical framework will comprise of the Navier-Stokes equation. This is the essential component, and on top of this, we may have different segments also be coming, heat transfer, mass transfer, solidification, etc., which may influence fluid flow. But basically, so far as the flow is concerned, in that case, we will have to solve the Navier-Stokes equation, and there we can take recourse of to the computational fluid dynamic softwares which are available in the market. Okay, let us now discuss a little bit about the boundary conditions and boundary types. That will give you some idea, because we will generate partial differential equations to predict fluid flow or melt flow in steel making systems, and these equations will invariably require initial and boundary conditions. And let us look at typical characteristics of various physical boundaries in say steel making reactors. So, always you will see that typically steel making reactors are going to be exhibiting solid walls which will form the boundary of the vessels. This is also solid wall. We have a free surface. So, 5 of our surface in most of the cases when you are talking of melt flow in BOF, ladle, tundish, mold, etc., 4 to 5 of our surfaces could be just the solid walls. For example, if you take the mold of continuous casting, you have copper cooled mold and we have 4 surfaces of the mold considered are the 4 physical walls or solid walls, and also we have a free surface. Free surface is a characteristics of steel making reactors. So, here because these are all batch reactors, you sometimes pour molten metal, you take out. So, you have a metal ambient interface all the time. If you look at tundish, so this is the free surface, these are the solid walls. So, here in tundish you have a frontal solid wall, back solid wall, 2 side solid wall and the bottom solid wall. So, you have 5 walls on the free surface, and on top of that you have a flow inlet and you have a flow outlet. These are the general characteristics of, for example, at solid walls we know that there can be no velocity. So, the velocities are going to be 0, no slip condition. At the free surface, if it is stagnant, we know that the vertical component of the velocity is going to be 0 because it is stationary, it is neither moving this way nor moving that way. Note that we have 3 components of velocity. So, on each of these surfaces, I have to write or provide boundary conditions on each of the 3 velocity components. This is very important for us to remember, but nevertheless inlet flows are known, outlet flows are also known in this particular case because I am considering a steady state scenario. So, therefore, height remains same. So, whatever is coming in is exactly same is going out. So, I will be knowing the velocities here, I will be knowing the velocities here, but I can, there is a standard outflow procedure also that you will come to know later on as you take more advanced courses. So, the boundary conditions here can be prescribed in terms of the known flow rate coming from the ladle. Here also it can be conveniently prescribed. We have solid walls, the boundary conditions are straightforward, that is all the velocity components are 0, and at the free surface we say that the normal to the free surface component is 0 and transverse gradient of the transverse components. These are the 2 transverse components on the free surface and their gradient is actually 0 at the free surface. Alternatively, one can also calculate the geometry of the free surfaces through some standard techniques and then impose the boundary condition, but these are really advanced things which I am not going to talk about here. Now, so we know the framework based on which the velocity field can be calculated. We have understood or we have at least appreciated the extent of complexity that is involved in calculating those. The equations that we generate are partial differential equations, and we, knowing the process, we should be able to provide the boundary conditions. So, there should not be any ambiguity as far as the key mathematical framework equations and boundary conditions are concerned in formulating fluid flow problem. Now, coming to the issue of turbulence, I mentioned that solving the Navier-Stokes equation for turbulent flow is little bit difficult. Now, the point is that I mentioned we cannot solve the equations that I wrote here, x component, y component and z component by analytical means. We have to solve the equations through numerical technique, So, therefore, when you solve the equation through a numerical technique, we are obliged to use suppose the reactor is there, I cannot have a continuous solution, but I have a discrete solution. I will select some points and then say that I wish to get the value of the dependent variable. The dependent variables in this case are the velocity components Vx, Vi, Vx, Vy, Vz. So, I want to have the velocity in some discrete location. So, I have a differential equation or a set of differential equations. I convert them into a set of algebraic equations. And how do I convert? I apply a numerical method. Okay. So, the essential purpose of the numerical method is to convert the differential equation into algebraic equation. Having obtained the algebraic equation, okay, and these algebraic equations are derived for certain points. So, the continuous information of the differential equation is now lost when we discretize the differential equation and derive the algebraic equations. So therefore, now I can have solution here, I can have solution here, I can have solution here, I can have solution here. So there are, how do I know these points? These are the points that the person who is solving he desires. For example, I can say I need only 16 points on which the velocity distribution is needed. Someone else may say, no, I don't want 16 points, I need 160 points. So the person who is solving the equations, it is he who decides, or the modeler or the person who calculates, he decides at how many locations he is going to need the constitute these points. So these points at which the solution is sought is termed as the nodal points or the grid points. Now we must understand that if you look at the structure here, so these are called the grid lines and the points are called the grid points. Now in turbulent flows, for example, you have eddying motions, and the size of the eddies, as you all know from your basic transport phenomena, can vary depending on where you are. You can have very small size eddies when you go towards the wall, you have big eddies in the bulk of the liquid. Now if we want to resolve the motion within the small eddies, then obviously these points need to be very close to each other. Okay. Now if I have a motion here, an eddying motion here, and the control volume is this big, okay, I will not be able to see that whether there is a gradient of velocity here or not here, because in this particular control volume, these nodes, it is a very big control volume and it has a characteristic velocity. So within this, so every nodal point here, to make it specifically, every nodal point is associated with a control volume, and the value of the Vx is assumed to be prevalent generally over the control volume, entire control volume. So if the size of the eddy is smaller than the control volume size, in that case the motion in the eddy cannot be resolved by the numerical grid itself. So therefore, when the flow is turbulent, when the length scales are very, very small, we are obligated to use points which are not like this, but the points which may be extremely close to each other. Then only we can have tiny control volumes, and these control volume size could be smaller than the size of the eddies, and therefore we should be able to resolve the turbulent motion accurately. If that happens, then what we are talking of a huge steel making reactor, 3 meter width, 3 meter depth. So you are going to have, if the sizes of the eddies are of the order of microns or millimeters, you can imagine that we can have millions of such nodal points, and at every point I have to solve equations which are nonlinear, multidimensional, and not such one equation. I have to solve 8 to 10 equations. So we will take an enormously long computer time in order to get a meaningful solution if we construct a extremely fine numerical grid in order to solve the fluid flow equations numerically. So therefore this solution is basically termed as the direct numerical solution in turbulent flow literature. Okay. So we will use Navier-Stokes equation, but construct a very closely spaced nodal points or grid points where we seek the solution, and then solve the Navier-Stokes equation and obtain the details of the turbulent flow. Solve the equations in an unsteady mode, because turbulence is rarely steady, it is a time dependent process. So therefore we will be constructing a very large number of nodal points, and as a result of which, as the number of nodal points are increasing, your computational task is also increasing. If I have, these are means there are so many unknowns to be known. In this case there are, so for example 4 into 3, 12 unknowns are to be obtained. In this case maybe there may be 4,000 unknowns, the way I have tried to draw the nodal points. There may be 4,000 or 5,000 nodal points within the domain itself. So finer is the grid or closer are these points, you will have to get more numbers, and therefore to get more numbers you have to do, the computer has to do more amount of computational work. So therefore when you are talking of a practical size domain, we will see that the computational time may be going to 1 month, 2 months or 3 months. So therefore as of now, with the largest computer on a routine daily basis, we cannot carry out DNS for steel making processes. So therefore the equation, Navier-Stokes equation, directly cannot be as of now applied. In principle, theoretically there is no problem, But because we face this practical difficulty, that because our computers do not have that large a power today, that we can obtain the direct numerical solution just like that in 5 minutes. No, it is not possible for such a big reactor. So, because of this constraint, we seek an alternative approach, and that alternative approach is called, I am just going to introduce this name and not discuss, which is called the RANS, the Reynolds average Navier-Stokes equation. So, some sort of averaging of the Navier-Stokes equation is done, and thereby the RANS equations are derived starting from the laminar flow equations or the exact Navier-Stokes equation. We derive the RANS equation, and this RANS equation then need a turbulence model. So, RANS equation plus turbulence model, then we can use such a sparse grid, there is no problem, okay, because we have averaged the behavior, okay, and we have other various techniques also. For example, there is a technique called LES, large eddy simulation. Just for your information, I am giving you the name, but the point that I try to make is that the Navier-Stokes equation, okay, with an extremely fine grid is still not a possibility for addressing all steel making problems. So, we try to look at an alternative way of predicting the flow in steel making reactor, and most commonly used approach is the Reynolds average Navier-Stokes plus a turbulence model. Okay. So, the moment you replace the Navier-Stokes, exact Navier-Stokes equation, now you have averaged it, you obtain the Reynolds average Navier-Stokes equation, but in that equation typically one sees that there is an unknown turbulent shear stress term. Say for example, these are the fluctuating velocity components, and this is the time average of the product of the fluctuating velocity component. So, this sort of a term comes when we time average this equation, and because this is now an unknown term. So, we have 4 equations, you remember you have 4 equations, 4 unknowns, but when we have time averaged it, additional unknowns come into the picture, and these additional unknowns are known as the turbulent shear stresses. And to calculate these turbulent shear stresses, because 4 equations, 5 unknowns means we cannot solve them, we have to specify these turbulent shear stresses somehow, and it is through the turbulence model that the turbulent shear stresses are prescribed. Okay? And we may have equations also, directly written conservation equation written for the turbulent shear stresses, but normally traditionally in steel making literature you will see that people have used turbulence model, and that turbulence model basically is the platform for calculation of the turbulent shear stresses. So, RANS equation and turbulence model equations are going to be used always as a RANS plus turbulence. This becomes our, they have to be applied in conjunction. So, our, as far as steel making is concerned, if you want to calculate the flow of melt in steel making reactors, in that case the fluid flow component, okay, or the flow model or the theoretical framework for melt flow calculation will comprise of the RANS equation, and along with this we will require a turbulence model, and the purpose of that turbulence model is to provide estimation or provide information on the distribution of the turbulent shear stresses. So, I repeat again that we have originally 4 unknowns u, x, u, y, u, v, u, z and p, and we have 4 equations, 3 conservation equation of motion and 1 continuity equation. So, the problem is well defined, but when you time average it, we still have 4 unknowns, those 4 unknowns, and on top of that we have additional unknowns which are turbulent shear stresses. So, unless these are prescribed, we cannot solve those 4 equations in a closed form, and therefore, how do you calculate this? How do you do this? This comes from the turbulence model. It is sufficient for you to know up to this particular point itself. So, therefore, we can say that a flow model for a steel making reactor will comprise of the Reynolds average Navier-Stokes equation plus the turbulence model. If you apply them in conjunction, you can obtain the time average velocity now, because this time averaging is because turbulent flow is what? The turbulent flow, for example, if you see a steady turbulent flow, for example, you can say that it goes random fluctuations are the characteristics of the turbulent flow, okay, and this is a steady state. So, if you put a probe inside a turbulent flow, in that case you will see that there are random fluctuations with high frequency, which is the characteristics of turbulent flow, and then this can be averaged, and this now represents what is known as the time average velocity. And when you solve the Rans's equation, you do not get the instantaneous velocity directly, you get an idea about the time average velocity, and it is this time average velocity you use in your melting rate calculation, mass transport calculation, two fluid interaction calculation, drag force calculation, and so on. One last point that I want to say, that this term, the Reynolds stress term, is essentially formulated in terms of, if you put a minus sign, then you can say the turbulence viscosity and the velocity gradient. So, we have if this is only meaningful velocity gradient is this dVx over dy. And this is now the time average velocity component. So, this is no more the unknown, this is as a part of, this is there in the Rans's equation. So, estimation of the shear stress, turbulence shear stress, essentially boils down to the knowledge of the turbulence, what is known as a turbulence viscosity. And this turbulence viscosity basically is a fictitious quantity. Do not confuse it with laminar viscosity. Dynamic viscosity or mu is a property of the fluid which depends on the state of the system. Pressure and temperature are constant, that means mu is constant. Mu t on the other hand is turbulence viscosity, and that varies from one point to another point in the system because it depends on. So, basically now going to the root of the problem, what does turbulence model do? The turbulence model actually provides us the distribution of mu t in the domain through an appropriate mathematical framework. So, we obtain mu t from the turbulence model, we substitute that mu t into the Rans's equation, then the Rans's equation boils down to 4 equations, 4 unknowns, and we are in a position to solve and obtain meaningfully the velocity field which are prevalent in the steel making.